In this video, we'll continue to look at CSEC Physics past paper questions. Now, in this video, we will basically look at another question. This time, I'm looking at a question on electricity, and this question comes from May June 2019 paper 2, question 5. All right, so let's begin. Now, the question says, a semiconductor diode is used in half-wave rectification. Sketch the IV graph for a semiconductor diode, and they would have given us the pair of axes with current in amperes on the y-axis and voltage in volts on the x-axis. So we have I in amperes and we have V in volts. Right? Now, before we sketch a graph, let's talk a little bit about semiconductor diodes. Now, a semiconductor diode essentially is a device which essentially conducts electricity in one direction. And that one direction is when it is said to be forward biased. So it does not conduct when it is reverse biased. Now, what exactly does it mean for a semiconductor diode to be forward biased? What exactly does it mean for it to be reverse biased? We'll illustrate by using simple circuits. So let's say we have a battery. We have a battery, which of course is a group of cells. The long terminal or the long stroke of the battery represents a positive and the short one represents a negative. And let's say we, to this battery or across this battery, we have a diode connected, a semiconductor diode, symbol for which looks like this. All right, so this will be the positive terminal of the battery, negative, and this is also the positive terminal of the diode, this is a negative. Now, in this setup, this is a simple setup, of course. If you're talking about building a regular circuit, we'd usually have a protective resistor and so on, right? But just for demonstrating what exactly it means to be forward bias and reverse bias and so on. Now, in this particular setup, we see that the positive terminal of the battery is connected to the positive terminal of the diode, and similarly, the negative terminal of the battery is connected to the negative terminal of the diode, and therefore, this diode would be said to be forward biased, and therefore, it would conduct. Right? So this is a forward bias diode. Good? Now, if we were to simply reverse either the diode or the battery, then it will no longer be forward biased and will now be reverse biased. So by simply reversing either the battery or the diode, all right, let's draw another diagram. So once again, let's leave the battery and we're going to reverse the diode. Right? So this is still plus, minus, minus, plus. So now, let's just basically try to show a current flowing there. Right? So now that we reverse the diode, what will happen is that the negative terminal of the diode is now connected to the positive terminal of the battery and vice versa. So the negative terminal of the battery is now connected to the positive terminal of the battery, of the diode rather, and this diode will now be reverse biased. Right? So because the diode is now reverse biased, it does not conduct any significant current. We tend to say it does not conduct any current, but in reality, it conducts a very, very tiny current, often called a leakage current, which is of the a few microamperes. So for that reason, when we plot this IV characteristic, we usually don't show any significant value on this side, where of course it is taken to be the reverse characteristic of the diode with a reverse bias, right? So basically, this is what it means for a diode to be reverse biased and forward biased, and the IV characteristic of the diode looks something like this. Right? So essentially, we could always draw to show that this is essentially zero, because if current is in amperes, then as I said before, it will not conduct any significant current when it is reverse biased, only when it is forward bias. And usually, even when it is forward bias, there is a small voltage which must be reached before the diode starts to do any significant conduction, and that voltage or the value of that voltage will depend on the material from which diode is made, right? So basically, this is what the IV characteristic of the semiconductor diode looks like. Now, the next part of the question, and that was worth basically 2 marks, right? The next part of the question, part B, says complete the truth table shown in table 3 for a NAND gate. So we're given a table and we're asked to complete it for a NAND gate. So let's just copy down that table. So that table shows we have inputs and we have outputs. We have two inputs, A, B, and we have the output C. So 0, 0, 1, 1, 0, 1, 0, 1. Right? So that is a table that we're given and we're expected to complete it for a NAND gate. Now, before we go ahead and try to do that, let's recall the logic symbol for a NAND gate and talk about its function or its operation. Right? So a NAND gate essentially looks like this. Right? So a NAND gate looks like this. So typically, let me just fix this a little bit. Right? So these, of course, would be the inputs A and B, and this would, of course, be the output C. Right? So this is what a NAND gate looks like. So essentially what a NAND gate is equivalent to we can call it a NOT AND, right? So essentially a NAND gate is an AND gate followed by an inverter, right? Usually we draw a NAND gate with two inputs, but of course you know that NAND gates can actually take multiple inputs, but at this level we usually restrict the number of inputs to 2, and of course it has a single output. So in reality, basically this can be further expressed to look like this. Right? So these, of course, would be our inputs, A, B, and this is our final output, C, because all of this together would be the NAND gate. So this symbol is equivalent to this, an AND gate followed by an inverter. Right? So in looking at the truth table, what we could do basically, get the output of the AND gate, let's call that X. And what would this mean now is that C would be not X, or we simply invert the values of X. So let's do that. Now, because this is an AND gate, basically our AND gate operates this. If the two inputs are high or ones, then the output will also be high. So in other words then, well, the output is high only if both inputs are high. Otherwise, it is a low output. So what this means is that if we were to put a little extra column here for X, since you introduce an X, then X would be 0, 0, 0, 1. So X would represent the output from the AND gate. But of course, we have an inverter, and therefore to get the output from the NAND gate, we're simply going to invert these values. So meaning that a 0 becomes a 1, and a 1 becomes a 0. So therefore, this becomes 1, 1, 1, 0. And this is basically representing the output from a two-input NAND gate. Right? So that is part B of the question. So let's make some space. All right, so part C of the question, it shows us three resistors of values 2 ohms, 5 ohms, and 10 ohms which are connected in series, right? And we're told to calculate the equivalent resistance of the resistors shown in the figure 5 above. Let's just represent the diagram. So we have a 2 ohm, so this is part C of the question. So we have a 2 ohm resistor, a 5 ohm resistor, and the third is a 10 ohm resistor. And we're asked to find the total resistance or the equivalent resistance of the resistors shown in the figure. So let's let the equivalent resistance be RT. Now, as we've examined before, whenever resistors are connected in series, then their total or equivalent resistance is simply the sum of the individual resistances. So if these individual resistances are, say, R1, R2, and R3, then RT is equal to R1 plus R2 plus R3, which gives us 2 plus 5 plus 10, which of course is equal to 17 ohms, right? So essentially, if you connect a 2 ohm resistor, a 5 ohm resistor, and a 10 ohm resistor in series, essentially what you're doing is creating a 17 ohm resistor, right? But of course, you know that resistors aren't always available in values like these. So oftentimes you may need to combine them, connect them in series to give a greater resistance that we actually need, since it's not necessarily available in a single resistor, all right? So that is part 1 of part C. Let's look at, let's continue with the question. So the equivalent resistance is 17 ohms, which basically means that these two resistors connected in series like this would be equivalent to a single 17 ohm resistor. All right, part 2 of C throws the same 3 resistors, but this time they're connected in parallel, right? So this was C part 1. Part 2 shows the same 3 resistors, but this time they're connected in parallel. So let's just represent that circuit. Right? So this is a 2 ohm, 5 ohm, 10 ohm. Right? So now the resistors are connected in series, and we're asked to find the equivalent resistance of the resistors in figure 6. So this is figure 6, that would have been figure 5. Right, so let's do this. So if you recall, whenever resistors are connected in parallel, the formula which relates the equivalent resistance RT is given by 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3, right? So 3 resistors connected in parallel, we use this formula to calculate their effective resistance RT. So we'll work out this value and then of course reciprocate it to find the value of RT. So let's begin. So this gives us, so 1 over RT is equal to 1 over 2 plus 1 over 5 plus 1 over 10, right? I guess you could always punch these values into your calculator, but since you have them on the board, let's do it the old-fashioned way. The LCM of 2, 5, and 10, that would be 10. So say 2 into 10 goes 5, 5 times 1 is 5, plus 5 into 10 goes 2, 2 times 1 is 2, and 10 into 10 goes 1, so 1 times 1 is 1. So therefore we get 1 over RT is equal to 8 over 10, and therefore RT is equal to 10 divided by 8, which gives us 1.25 ohms, right? So the equivalent resistance of these two resistors connected in parallel is 1.25 ohms. So let's examine these two situations. So we saw that whenever we connected them in series, their values are simply added to give the total equivalent resistance. So essentially, if we have resistors and we want to provide a greater resistance in a particular circuit, we'll simply connect them in series. However, if we desire to produce something which is smaller than each of the individual resistors that we have, we must connect them in parallel, right? So the effective resistance is 1.25 ohms, and if you notice, that value is actually even smaller than the smallest value of the 3 resistors that were connected in parallel, and that is generally a characteristic of the equivalent resistance of resistors connected in parallel, right? So if you have 3 resistors or any number of resistors connected in parallel, their equivalent resistance will always be less than the smallest value of those resistance that are connected in parallel. So in other words then, if you connect a 2 ohm, a 5 ohm and a 10 ohm resistor in parallel, and when you work out the equivalent resistance, you're getting something like 3.2 or 3.1 or 2.5 ohms, then know that you made a mistake, because equivalent resistance cannot be greater than the least resistor which were connected or which was connected in parallel. Right? So that was part C2 of the question. Let me see if there's any other part. There should be. Right? So 4 marks for that. So next part 3 says the resistors in parallel shown in figure 6 above was connected in a circuit to a 6-volt battery, so a 6-volt power supply. Calculate the total current flowing through the circuit, right? So let's just modify our diagram to show that. So this is now part 3. So let's just change this to, anyways. All right, so this is the circuit that we had before. And let's now basically connect a battery to this. So let's just put the battery here. Let's put the battery. All right, let's just put the battery down here somewhere. Well, let's say it's a power supply, but let's just use a battery symbol for a battery, right? So this is 6 volts, right? So what's going to happen? Well, essentially, the battery is going to drive, or the power supply is going to drive a current I. Right? The current I will flow. Let's label this junction. Junction A, junction B. Now, all of what we're doing here is not required by the question, but I'm just doing it to explain some of the principles behind these connections, or these circuit connections, right? So this battery, positive terminal, negative terminal, right? Remember that whenever you draw circuits, the conventional current, which is what we need to show in circuits, is basically flowing from the positive terminal of the battery or the power supply. So this battery is driving a current I, which comes to this junction A at A. At this junction, the current sees multiple paths. It sees a path to the 2 ohm resistor, the 5 ohm resistor, and the 10 ohm resistor. And what the current will do is that it will actually split, and the portion of it will flow through the 2 ohm, another portion will flow through the 5 ohm, another portion will flow to the 10 ohm. So we can call these, for instance, I1, we can call this one I2, and we can call this one I3. And what happens is that, of course, the sum of these individual branch currents will add to give the total current. Now, we're not required to calculate these individual currents, but we can speak about their relative magnitudes, right? Now, electrons, which essentially are responsible for the electric current, often or always try to take the path of least resistance. What exactly does that mean? If there are multiple paths, and different parts have different resistances, then more electrons will actually flow towards the path of least resistance. In other words, then a larger current will always flow towards the path of least resistance. So in this particular case, the 2 ohm resistor will have the larger current flowing through it. Then we'll have the 5 ohm resistor having the next largest current, and of course the 10 ohm resistor will usually have the smaller current due to the fact that its resistance is the greatest of the 3, right? So let's just now proceed to calculate the total current. Now, since we calculated the total or the effective resistance of this combination from part 2, of course we'll be using it. So we have RT is equal to 1.25 ohms. So this is part 3 of the question. So we have the total effective resistance RT is equal to 1.25 ohms. And we have the power supply, let's call that E, or let's call that, so supply is 6 volt power supply. So because it's a 6 volt power supply, and of course these resistors are connected in parallel, the PD across them will be the same and will be equal to the power supply voltage, right? So therefore the PD across them, V, is equal to 6 volts. By Ohm's law, we have the equation V is equal to IRT, and from that, of course, that means that I is equal to V over RT. So therefore, the current flowing I is equal to 6 volts divided by 1.25 ohms. And what does that give us? I'll have to go to my 1.25. Is that? No, that's not 4. 6 divided by 1.25. Well, 4.8. So therefore that gives a current of 4.8 amperes. Right? So when this 6-volt power supply is connected to this circuit, where we have the 2 ohm, 5 ohm, and 10 ohm resistors connected in parallel, then the total current which is being driven by this power supply will be 4.8 amperes.